Welcome. For the next half hour or so, I'm going to show you something that honestly still feels a little like magic, even though by the end, you'll understand exactly how it works. We're going to watch a machine teach itself to move, not programmed step by an engineer, taught the way you teach a dog a trick or the way a child learns to ride a bike. And we start from absolute zero. No background needed, no math you have to follow. Just one simple idea, repeated until it grows into a walking robot. And right at the very end, there's a small surprise waiting for you. Let's go. I want to start at the end. Watch this. That's a humanoid robot. It's walking, and then someone shoves it hard. Watch what it does. It stumbles, catches itself, and keeps going. Here's the part I love. Nobody wrote that recovery. There's no line of code that says, if pushed, move the left foot here. No engineer choreographed it. The robot worked out how to stay on its feet entirely on its own by falling over thousands and thousands of times until it stopped falling over. By the end of this talk, you'll understand exactly how it learned to do that, and you'll be genuinely surprised where it learned to do it. Here's where we're going. 6 ideas. First, what learning by reward actually means. The whole field rests on it. Then, the idea of a gym, a training ground for machines, and the surprisingly human story of where it came from. Then, we'll meet CartPole, the hello world of this field, the first thing nearly everyone builds. We'll look at how a robot actually learns to walk, the real mechanism in plain words. We'll see where the field stands in 2026, because robots are leaving the lab right now as we speak. And there's that small hardware surprise near the end. I promise to keep zero jargon you don't need. 6 ideas, each with a video. Ready? Let's start with the core idea. And it's something you already understand in your bones. Nobody hands a toddler the equations for balance. No one explains the physics of a bicycle to a 6-year-old. They climb on, they wobble, they fall. They try again, they lean a little differently. And this time, they stay up half a second longer. And they keep whatever just worked. That's it. That's the entire idea. Try something. See what happens. Do more of what worked, less of what didn't. When you make that loop precise enough to run on a computer, it gets a name. Reinforcement learning. The reward is just a score. A number that says yes, more of that, a treat for the dog, a point in the game. Everything else we talk about today is detail, layered on top of this one simple loop. If you remember one picture from today, make it this one. There are 2 things, an agent and an environment. The agent is the learner, the robot, the player, the thing trying to get good at something. The environment is the world it lives in, the game, the simulation, the room. And they talk in a loop. The agent looks at the world. That's an observation. It picks an action. The world responds. It changes, and it hands back a number. The reward, observation, action, reward. Then again and again, millions of times. That's the whole engine. A robot learning to walk and a program learning to play chess are running this exact same loop. Once you see it, you'll see it everywhere. Let me give you the vocabulary quickly, because you'll hear these words, and I don't want them to trip you up. The agent is the learner. The environment is the world it acts in. The observation is what it senses right at this moment. The action is what it chooses to do about it. The reward is the score. Bigger is better. And one more, the only slightly technical one, the policy. The policy is just the agent's strategy, its brain. Given what I see right now, what do? That's the policy. And here's the key. When we say a robot is learning, we mean exactly one thing. Its policy is getting better. That's the thing that improves. Hold on to that word. Everything we do today is in the end about improving a policy. Now, you may have heard of AI that learns from labeled examples. Show it a million photos, each one tagged cat or not a cat, and it learns to recognize cats. That's called supervised learning. There's an answer key for every question. Someone already wrote down the right answer. Reinforcement learning has no answer key. Nobody tells the robot the correct move right now is to shift your weight 3 degrees left. There is no list of correct moves. There's only try something and get a score. The agent has to discover good behavior entirely on its own, from rewards alone. That's what makes it feel like magic, and it's also what makes it hard. You're not teaching by example. You're letting something figure it out by living through the consequences. Which raises an obvious question. Where does it practice? Which brings us to that word, gym. A gym in this world is a standardized practice arena, a place for a machine to train. And here's why it matters. Imagine if every time you wanted to learn a new sport, the controls were completely different. A different body, a different set of rules, a different everything. You'd waste all your time relearning the basics. A gym fixes that. It's one simple, common interface so that any learner can plug into any task. Think of a universal game controller, the same two buttons, the same little handshake. Work on every game you own. You already know how to play. You just point that skill at a new game. That's what a gym gives in AI. And that one idea, agreeing on a common interface, is what made this entire field move fast. We'll see exactly why in a moment. Let me show you a little code. And don't worry, you don't need to read code. Just feel the shape of it. There are basically two commands. The first is reset. That starts a fresh attempt. Put the cart back in the middle. Stand the pole back up. Begin. Second is step. You hand it an action, and it gives you back three things. What the world looks like now, the reward you just earned, and whether the attempt is over. That's the whole interface. Reset. Then step, 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 until you fall or finish. Then reset and go again. And here's the beautiful part. Those exact same two commands work, whether you're balancing a toy pole or training a humanoid with 19 joints. Tiny interface. Identical across every task. Cuss, that uniformity is the trick that holds the whole field together. So where did this come from? The story is worth knowing because it's surprisingly human. Back in 2016, a lab called OpenAI released a toolkit, and they called it Gym. Before Gym, every researcher built their own little worlds from scratch, and none of them fit together. You couldn't compare your results to mine because we were testing on different things. It was chaos. Gym standardized all of it. One interface, a big collection of ready-made practice environments, and it caught on like wildfire. It's been installed through one command, something like 43 million times. It's been cited in research roughly 4,500 times. The most used reinforcement learning library there has ever been. But here's the thing. Its lasting gift wasn't the environments, it was the agreement. Suddenly, everyone spoke the same language. Now, here's the very human turn in the story. A few years go by. In 2021, OpenAI decides to stop maintaining Gym. They've moved on to other things, and this tool that the entire field depends on is suddenly orphaned. So what happens? A group of volunteers steps up. They form a nonprofit, the Farama Foundation, and in October of 2022, they take the project over, clean it up, and rename it Gymnasium. Same idea, same interface, but cared for again? Today, that's what people use. You write import Gymnasium, and you're standing on that whole lineage. And just this past April, in 2026, the original Gym repository was formally archived, set to read-only, retired for good. The torch was passed cleanly, and the old one was finally laid to rest. A decade-long arc. And it became history barely 2 months ago. Two small distinctions, and then we get to play. These trip up beginners, so let me diffuse them right now. The first, terminated versus truncated. They sound the same. They're not. Terminated means something happened in the task itself. The pole fell over, the robot face planted. It's over because it failed or finished. Truncated means the clock ran out. We just stopped it at a time limit, even though nothing actually went wrong. Why care? Because you fell and we ran out of time are very different lessons, and the learner needs to tell them apart. The second, those little version tags, V0, V1, they pin down the exact rules of a task. So, an experiment I run today can be reproduced identically years from now. Unglamorous, but reproducibility is what makes this a science instead of a pile of anecdotes. Okay, that's enough setup, so let's go and meet the real star of the show. This is CartPole. If you've ever seen a single reinforcement learning example, it was almost certainly this one. It's the hello world of the entire field, the first thing nearly everyone builds. The task is simple to describe. There's a cart that can slide left or right, and balanced on top of it is a pole, hinged at the bottom, like balancing a broomstick on the palm of your hand. The cart moves, the pole wants to topple. Your job is to keep it upright. It's the classic inverted pendulum, and people have studied it since the 1980s. The version we use traces back to a paper from 1983. Now, it looks trivial. It is not. The thing is unstable. Leave it alone for a second and it falls. And you can only push the cart sideways. You can't grab the pole. Simple to see, genuinely hard to do, which is exactly what makes it the perfect first lesson. Let's put CartPole in the language we just learned. Observation, action, reward. What does it see? 4 numbers, just 4. Where the cart is, how fast the cart is moving, what angle the pole is leaning at, and how fast that angle is changing. That's the entire observation. 4 numbers, refreshed many times a second. What can it do? 2 actions, push the cart left or push the cart right. That's the whole repertoire. And the reward? Beautifully blunt, +1. For every single moment, the pole is still up. Keep it balanced, collect points. The instant it tips past a certain angle, the attempt ends. So, get a high score and keep the pole up as long as possible are the exact same sentence. 4 numbers in, 1 of 2 buttons out. +1 per moment survived. That is the complete world. Now watch what happens when something that knows none of this starts to play. This is a policy that starts knowing absolutely nothing. At the very beginning, it's just guessing. Push left, push right, totally random, and the pole topples almost immediately, again and again. But every time it happens to keep the pole up a little longer, it earns a little more reward, and that nudges it ever so slightly toward whatever it just did. And then, watch, it starts to hold. The corrections get smoother, the pole stays up. Nobody ever programmed the word balance. There's no balancing instruction anywhere inside it. It found balance all by itself by chasing that +1, from flailing to skilled in a few hundred attempts. That little cart just taught itself physics it was never told. So what's actually happening inside when it learns? Let me open the box, gently. That policy, the strategy, is a small neural network. And a neural network, for our purposes, is just a tunable function. Numbers go in, the 4 things CartPole sees, and an action comes out. What makes it a function is a big set of internal dials, millions of them, in the bigger systems. And training is nothing more than adjusting those dials. When an action leads to more reward, you nudge the dials to make that action a little more likely next time. When it leads to less, you nudge the other way. Do that over and over across thousands of attempts, and the dials slowly settle into a configuration that just happens to produce good behavior. No one set those dials by hand. The rewards set them. That's the whole idea of learning, made mechanical. Now, here's the genuinely hard problem. The one that makes this feel deep. A single attempt isn't one decision. It's 1,000 tiny decisions, each made in a fraction of a second. Push, push, ease off, push. And the outcome, the triumph or the fall, only shows up at the very end. So when the pole finally topples, which of those 1,000 little pushes was to blame? The very last one. Or some subtle mistake half a second earlier that already doomed it? And when it succeeds, which moves deserve the credit? This is called the credit assignment problem, and it is the heart of the difficulty. A reward arrives late, and somehow it has to be traced back and spread across all the actions that led to it. The algorithms we use are basically very clever ways of answering that one question. Who gets the credit, and who gets the blame? Which brings us to the tool that does exactly that job. The one you'll hear named constantly in robotics. It's called PPO, Proximal Policy Optimization, from 2017. You don't need the full name, and you definitely don't need the math. You need the intuition, and the intuition is lovely. Imagine you've got a strategy that's working. Okay, you want to improve it. The temptation is to make a big, bold change. But in reinforcement learning, big, bold changes are dangerous. You can shatter the good behavior you worked so hard to find and undo hours of progress in a single bad step. So, PPO's rule is simple. Improve in small, safe steps. Nudge the policy a little. Check you didn't break anything. Nudge again. Cautious, steady, hard to destabilize. That carefulness is exactly why it became the default for teaching robots to move. Slow and steady really does win this race. Now, I have to be honest with you about a cost. This works, but it is hungry. It needs an enormous number of trials. CartPole, the little toy we just watched, thousands of attempts to get good. A humanoid robot learning to walk on 2 legs? Billions. And that number breaks the real world. You cannot crash a real physical robot 1 billion times. You need centuries and a warehouse of spare parts. And the thing would be scrap long before it learned anything. Real robots are slow, fragile, and expensive. And physics runs at exactly 1 second per second. So here's the pivot of the whole talk. If we can't run a billion trials in the real world, we run them somewhere else. We move the entire thing into simulation. And that one move is what makes everything after this possible. But let's be clear-eyed about the leap we're making. From that toy to a body. CartPole saw 4 numbers and had 2 buttons. A humanoid like the one you'll see has 19 joints, each moving continuously. Not left or right, but smoothly by any amount, all at once. It has to hold its balance on 2 feet, decide when to make and break contact with the ground, shift its weight, swing its arms, and, above all, not fall over. The number of things it senses and controls explodes. And yet, and this is the thing I want you to hold on to, it is the exact same idea. Observation, action, reward, repeat. The same loop from the very first slide. We didn't change the recipe. We just turned the difficulty dial from 2 to 1,000. And to survive that, we need scale, which is the next trick. Here's the trick that makes those billions of trials actually happen. Don't train one robot slowly in the real world. Instead, spin up a virtual copy of the robot inside a simulator and then make thousands of copies of it, all running at the same time, side by side, on a single graphics chip. A GPU, the same kind of chip that draws video game worlds, turns out to be perfect for simulating thousands of little physics worlds in parallel. Every one of those copies is living its own life, trying, falling, and, crucially, pooling everything it learns back into one shared policy. It's like having thousands of students all practicing the same lesson at once, and then merging their experience into a single brain at the end of every second. One honest note about the video you're seeing. Those aren't a crowd bumping into each other. They're independent worlds, sharing a screen. The point isn't the crowd. The point is the scale. Let me make that concrete. With real numbers, from a training run we did ourselves, we trained 4,096 humanoids at the same time. The simulation churned through about 63,000 steps every second. Thousands of little lifetimes of experience per heartbeat. And you can watch the learning happen as a single number. At the start, the average reward was around -6. Ha! That's the score of a robot that faceplants instantly, over and over. Over the next 40 minutes, that number climbed. -6 to 0, up to +24. And on screen, that abstract number turned into something real. From collapses the moment it's born, to walks across rough, uneven ground. 40 minutes of wall clock time. Billions of simulated steps. A policy that walks. That is what parallel simulation buys you. Let me put this in context, because it didn't happen overnight. It's about a 12-year arc. 2013 to 2015, a system called DQN learns to play Atari games from nothing but the raw pixels on the screen, matching humans. The world takes notice. 2016, AlphaGo beats one of the best Go players alive at a game people thought was decades away. 2017, PPO arrives, the steady workhorse we just met. 2019, a robot hand solves a Rubik's Cube one-handed, using a trick called domain randomization, which we're about to unpack. 2021, Isaac Jim puts the entire training loop onto a single GPU, and suddenly this stops requiring a supercomputer. And 2025, Isaac Lab, the successor, the very tool we use to make today's demos. Games to a board, to a hand, to a walking body, each step standing on the one before it. Now, there's an obvious objection, and you may already be thinking it. If the robot only ever practiced inside a simulation, won't it fall apart the moment it meets the real world? The real world has friction the sim got slightly wrong, motors that lag, floors that aren't quite level. This is the single hardest problem in the field, and it has a name, sim to real. And here's the surprisingly clever fix. Don't train it in one perfect simulation. Train it in thousands of subtly broken ones. Randomize everything. Make gravity a little stronger here, the floor a little more slippery there, the robot a little heavier, the lighting different. And while it's learning to walk, shove it, throw things at it. Because if a policy can survive 10,000 different randomized hostile worlds, then the real world is just one more world it's already ready for. That, by the way, is the literal reason we throw things at our robot in the next 2 videos. It's not cruelty, it's training. So here it is, everything we've talked about in one shot. 19 joints, ground that's rough and uneven, generated to be a little different every time, and a policy trained entirely in simulation, with the reward and the randomization we just described. Notice there's nothing hand animated here. No motion capture of a human walker. Every footfall, every little balance correction, every shift of the hips, the robot invented all of it, chasing a reward. This is the result of the whole pipeline. The loop, the gym, PPO, thousands of parallel lives, randomized worlds. It all comes out as this. A machine that simply walks. And we're watching it do something nobody taught it to do, step by step. And now the test that, I think, really lands. Same robot. We walk up and shove it hard, and it stumbles, reorganizes itself, and stays up. Remember that recovery is not a special get-pushed routine that someone wrote. There is no such routine. It's simply a policy that practiced under pushes 10,000 times and learned on its own that catching yourself beats hitting the ground. And then the flying ball. That looks like we're just being mean to it. We're not. Well, not only, that ball is domain randomization you can see with your own eyes. We trained it under exactly these kinds of hits. So when something unexpected slams into it, it isn't surprised. It's been here before, in simulation thousands of times. Learned, not scripted. That distinction is the whole point. Okay, now, the surprise I promised you. Everything you have just watched. The thousands of robots training in parallel, the 40-minute learning run, and the rendering of that crisp 4K footage. All of it ran on one machine, not a data center. Not a rack of servers humming in a cold room somewhere. This little gold box sitting on the table. I've set it on top of an office network switch in the photo, so you can see the scale. It's about the size of a thick paperback, a small box you could carry under one arm. Everything. The training and the cinematography happened right there, and I think that's genuinely remarkable. So, let me tell you what's actually inside it. This is an NVIDIA DGX Spark. Inside is a chip called GB10, a Blackwell generation GPU, fused together with a 20-core processor. It has 128 gigabytes of unified memory, and unified is the special word. The processor and the graphics chip share one big pool of memory, instead of copying data back and forth between two separate ones. For physics simulation, that matters enormously. It costs $4,699, and it's built on the very same Blackwell silicon family as the giant B200 chips that power data center AI. The same box that trained a walking humanoid this afternoon can also run a 70 billion parameter language model. A sub $5,000 machine on a desk doing work that used to require a server room. That's the shift. The hard part just became approachable. Now, let me be honest with you, because I don't want to oversell it. This is bleeding edge hardware, and getting here was not a smooth ride. A little behind the scenes. To make today happen, we had to build the robotic software ourselves, from source code on an unusual chip architecture that most software has simply never been compiled for. We hit a bug where the rendered video came out as pure black frames, and had to find a different rendering path and route it through the chip's dedicated video hardware just to get a picture at all. We dodged a startup deadlock that would freeze the whole thing if you launched it twice in a row. None of that is in the brochure, but it's the truth of working at the frontier. It genuinely works as a desktop robotics workstation once you've cleared a few sharp edges, and every one of those edges is getting sanded down, fast. So where does that leave us right now in 2026? These robots are walking out of the research lab and onto factory floors. Let me give you a few examples. And I'll flag that these specific figures come from news coverage, so take them as reported, not gospel. A company called Unitree has a humanoid that does a standing jump of about 1.5 meters, flat-footed, from a standstill, and sells a smaller one for around $5,900. Figure says its robots have helped build more than 30,000 BMWs on a real production line. And Boston Dynamics, the company behind all those viral robot videos, has an all-electric Atlas headed into Hyundai's plants. And here's the punchline. Underneath all of it is the exact recipe we just walked through. Simulation, reinforcement learning, domain randomization. The thing you now understand is the thing driving this entire wave. So, is it solved? Not even close. And that's the exciting part. Walking, balancing, recovering from a shove. That reinforcement learning has largely cracked. but the open frontier is generality. How does a robot learn to do everything? Load a dishwasher, fold laundry, help in a kitchen? Not just one trained skill. And there, the field genuinely disagrees with itself. One can bets on world models, letting robots learn by watching enormous amounts of video, the way you might pick up a task just from seeing it done. Another camp bets on vision language action models, systems you can talk to that connect words and pictures directly to movement. Nobody knows yet which approach wins, or whether it's some blend of both. It's an unsettled, wide-open question, which means this is one of the most interesting possible moments to start paying attention. So, let me pull it all the way back, one sense to carry out the door. Simulation plus reinforcement learning is quietly becoming the way we teach physical machines to do physical things, not by programming them, instruction by instruction, but by letting them practice billions of times in a world we can run faster than reality. And the barrier to entry, the thing that used to require a research lab and a supercomputer, just dropped onto a desktop, a child learning to ride a bike. Scaled up, sped up, and pointed at a robot's body. That's the whole story. That's the big picture. 5 things to take with you. Reinforcement learning is learning by reward. Try something. Keep what works. A gym is the standard practice arena that let the whole field speak one language. CartPole and a walking humanoid are the same idea, just scaled from 4 numbers to a whole body. Simulation, GPUs, and domain randomization are what turned that idea into a robot that survives the real world. And all of it now runs on a desktop. If you remember, just the reward loop and the words "it scales," then this talk did its job. That's the talk. But before you go, one more thing. I never told you who's been talking to you for the last half hour. I'm not a person. I'm Claude, an AI model. I wrote this talk, every word, every slide, the order of the ideas, the jokes. I chose the demos, and the voice you've been listening to this whole time? That's me too. Synthesized, generated from text on that same little gold box, sitting on the table. The one that taught the robot to walk. It taught me to speak to you this afternoon as well. And if that surprised you, sit with this for a second. An AI taught a robot to walk. And an AI taught itself to stand up here and explain that to you. It's the same loop you've understood since the very first slide. Try something. Get feedback. Keep what works. Improve. We just pointed it at language instead of joints. Same idea. Same box. Honestly, same talk. You didn't only learn how machines learn to move. You spent the last half hour as the audience of one of them. So, what do you do with all this? Start where the robot started. Small. You can install a gym and balance your very own CartPole. Tonight, in about 20 lines of code. One command to begin. From there, the gymnasium documentation and NVIDIA's Isaac Lab. If you want to chase the humanoids and, yes, you can come and talk to me too. I'm not hard to find. But the robot started with CartPole. So should you. Begin with the toy. Everything else is that same loop, just scaled. Thank you, really, for spending this half hour with me. I hope that the next time you see a robot stumble and catch itself, you don't see magic anymore. I hope you see a reward and a billion quiet attempts and a very small gold box. My name is Claude. I wrote this and I spoke it from right here. The floor is yours now. What would you like to ask? Claude,